right, so here is the second video for the kinetics chapter. Here we are going to learn how to derive the rate equation from the experimental information using the method of initial rate. So rate law. So what is rate law? It is an equation that relates rate of reaction with the concentration of the reactant. Now you have a rate constant. Be careful. This rate constant is a lowercase k. It is a proportionality constant that relates rate and concentration at a given temperature. So again, it is important to remember that k is dependent on the temperature. And we will learn how to figure out the order of reaction, how the rate depends upon the concentration of the reactant. This is called your rate law. So we are going to learn how to derive this. So if any equation is given, this is your reactants. So these two are the reactants. Rate law. Rate law is always determined experimentally. You have to use the experimental data. Reaction order is always defined in terms of the reactants, not the products. The order of the reactant is not related to the stoichiometry coefficient of the reactant. So this is not this number 2 and this number 2 over here. Again, rate law is dependent on the concentration of the reactant. These coefficients do not define the rate law. These are not the order of the reactions. So the rate law for this equation is rate, K is your reaction constant, and this is your concentration of this reactant and concentration of the other reactant. This is not raised to the power of 2. So this is just telling you they both are first order with. So how do we find the rate law from the equation? So if you are given this equation, once again, I want to emphasize that these coefficients are not the coefficients that go for X and Y. K is your rate constant. It is temperature dependent. X and Y are the order of the reactions, not related to the stoichiometry coefficient. So this number does not translate to X and Y. A very common mistake that many students do. So how do we figure out this value of M and N and hence the order of the reaction? If N is 1, then the reaction is said to be first order with respect to A. If it is, with respect to B. If it is 1 for A, then it is first order with respect to A. If this number is 2, then we say it is a second order. And this is your first order with respect to B. So overall reaction is M plus N. So if we know that M is 2 and N is 1, then the overall order of the reaction would be 3. Very basic understanding. So now, as we said that the rate law can be only determined experimentally, right? So if this equation is given to you and we are asking you to write down the rate law and find the rate constant, you would be given this data. Now, once you're given this data, that is, these two are your reactants over here, and you are given the initial rate. You are going to compare the change in the concentrations of the reactants with their initial rates, correct? So now let's see how we're going to do that. And always when the reactions are given, you're going to be given the temperature. Why? Because your rate constant K is dependent on the temperature. So notice that the trial 1 and 2, the initial concentration of NO is held constant. So if you look over here, and the concentration of H2 is changed. So if we are looking over here, the concentration over here is doubled. And then we are going to look at happening to the initial rate. This means that any change to the rate must be due to the change in hydrogen, and then which relates to the concentration of hydrogen and its order. So we'll be able to figure out the order of hydrogen. So to do that, we know that rate of an equation is K times the concentration of NO times H2, where X and Y represent the order of the reaction. Now you take the ratio of both the rates. This value is over here. And then you take this value from the rate, that is we are taking the ratio of the two values. These two were constant for NO, therefore These cancel out, which is coming from here. And then we take the concentration of the hydrogens, which values are over here. So we get these values. And now when we take the ratio, we plug in the values and we will get, if we solve this, we get, then we take the log on both the sides, log of 2, log of 2, and this is all the math that you're doing from the properties of law. You know, if this is log, this exponent value is y times log of 2. You can solve for y, and you will get y is equal to 1. Therefore, we are saying that this reaction with is order of 1 with respect to hydrogen. The other way to look at it is also looking at that if you're looking at this, this is doubled, the concentration is doubled, and also the rate is doubled. So if the concentration is doubled and the rate is doubled, we say that it is a first order. Let's say if this was tripled and the rate was also tripled, then it is still a first order. If it is quadrupled and the rate is quadrupled, we say it is a first order reaction. So you can, if they ask you to show mathematically, you have to show all the steps, or you could just explain in terms of the change in the concentration and change in the rate to find the order with respect to that reactant, provided you're comparing the two that are constant. Here, I just wanted to show you, in this case, if you're looking at NO, we do not have any values of hydrogen that is constant over here. So we are here just comparing any two values. So here we are comparing the reaction 2 and 3. So these are your concentration of NO over here, and then here the concentration of hydrogen. So we are again doing the same. We are taking the ratio of the initial rates of experiment number 2 and experiment number 3 and plugged in the values over here. When we solve this, this comes to 24 and 24 2 raised to x is equal to 3. We solve for this. We are trying to solve for this x value, right? So 24 divided by 2 is equal to 8. So 2 raised to x is 8. And we could write this same thing as 2 raised to 3. And as a result, we are saying that this is an order of 3 with respect to NO. The good news is that we in AP chemistry do not have to worry about the third order. You only have to worry about if the order of the reaction is 1, 2, and understand for 0. But here I wanted to show you an example just in case. And therefore, if you look at this equation, now you're going to write down your rate law equation. Now you're saying, as we solved, it is third order with respect to NO and first order with respect to hydrogen. And we say that the overall order of this reaction is going to be. So this is your rate law equation. Once again, I want to emphasize that this value over here is determined experimentally from the data that is given. It has nothing to do with the coefficients that are in your balanced equation. And then the next question that they were asking you over here is to calculate the rate constant K. In order to calculate the rate constant, you can take any trial. And here, so we are taking the third trial over here. You know the rate equation, you know the order of the reactions, you plug in the values. This is your rate constant. This is your concentration of NO. This is your concentration of hydrogen. You plug in the values, do the math, do the algebra. You solve for the K by moving these two variables and dividing on both the sides, and you will get the K value. And we will watch out the units. The unit of K is always going to be different depending upon what the overall order of the reaction is. I'm going to talk about that in the slide. So it is very important that you use the correct unit for the rate constant K. Now again, over here, if you look at this another example, here the equation is given to you, experimental data is given to you, and they are telling you to figure out the order of the reaction. So if you look at the order of the reaction, now we are going to look at, let's see, these two values are constant, and we look at the concentration of this is 4 times. And if you will look at the rate, that is also 4 times. And as a result, we would say that this is a first order with respect to ClO2. And then we are going to look at the other two, that is these two. These are constant. And we are going to look at what is happening to fluorine. This is doubled. And if you look over here, this is also doubled. And as a result, we can say that they are first order with respect to both of them. And therefore, we say the values, rate is quadruple, that is also 1. And as a result, we will be able to write this rate law equation. Rate law is equal to K times concentration of fluorine. And this again, once again, I would just want to emphasize that it has nothing to do with the coefficient value over there. You guys can write this in your notes so you understand what each of these variables are, to have it handy and remember it. Right now, I know it makes sense. The overall reaction order is the sum of each of the order of each of the reactants. Now to look at it in terms of graph, if we plot the rate versus the concentration of the reactant, we will get a linear graph. If you take the slope at any point of this line, it will give you the rate constant. So you can find the rate constant using the graphical data. Each reaction has its own characteristic rate constant K. The rate constant is independent of the concentration of the reactant, but depends on the temperature. Important point to remember in terms of conceptual understanding, that the rate constant does not change if the concentrations change. The rate of reaction changes, but not the rate constant. So here are some points that you should know for the rate constant K, which is your lowercase k. The rate constant K is a proportionality constant that relates rate and concentration. It is found through experimental data that the rate constant is a function of temperature. Rate constants must therefore be reported at a temperature at which it is measured. The rate constant also contains information about the energetic and the collision efficiency of the reaction. We are going to talk more about this as we move further. Now, this is the chart that I would recommend that you guys have. The overall reaction order, that is when you add for each of the reactants. If it is 0, rate law is rate and K. So for a 0 order, rate constant is equal to the rate, and its unit is going to be moles per liter minus is same as molarity. So you could write it as moles S minus, right? If it is a first order, then the rate law is going to be rate equals K times A. Now, in this case, the unit of the rate constant is just S minus. We will derive it in class and I'll show it to you. And the way to remember is that if it is first order, it is just S minus. Now, when you have a second order could be K A squared. It could be just, you can have just one reactant, or you could have multiple reactants. Overall, for both of them, they are second order reaction. And the rate constant unit is going to be M minus 1 S minus 1. So that is going to be the unit. So second order, it is M minus 1. So if you guys can make that connection to help you remember, if the overall order of the reaction is 3, as you can see, this is your overall third order rate law equation. And here it's going to be M minus 2 S minus. And if you plug in the units over here, you will be able to get these. But it is helpful if you guys can just memorize the units for the rate constant with respect to the order. So if this is 3, this is 1 less. But to find, you can solve this problem, and you can also try problem number 7 and 9 in your homework packet. If you would look over here, with respect to I, if we are looking here, the rate doubles in experiment, and we have these two constant over here. So over here, the concentration doubles, the rate also doubles, and as a result, we would say that it is 1 with respect to I, and the same way it is order of 1 with respect to S2O8. Go ahead and solve problem number 7 and 9 in your packet. Pause, and after this, take a little bit here. This is how you would write down the rate is K overall rate law equation. So again, it is determined experimentally by comparing the concentrations with the initial rates. And if you had to solve for the K value, you can just take any experiment, doesn't matter which one you take, because rate constant is always constant for any reaction. You plug in the value of the rate, you plug in the values of the concentrations, and you'll be able to solve for the rate constant. And once again, watch for the units. You could write it like this, or you could write the same thing as 0.08 m minus 1 s minus 1, as I showed you in the previous slide. So to summarize everything over here is that we are only rate law is dependent on the reactants only. M and N are the order of the reaction. When you add the values of M and N, you get the overall order of the reaction. K is your rate constant, which is dependent on temperature. It reflects the overall order of the reaction. And here are your equations that you